Yep. Okay. Can you hear me now? Okay. Yeah. All right. And then we have, okay, so that'd be 9 plus 9, so that would be 18. All right, and then we do want to not have a negative exponent, so we take that one down. So we end up, 4a to the 12th, c to the 18, all over b. All right, and this does say evaluate. So I'm going to multiply the exponents. So 4 times 2 is 8, so that'll be 2 to the power of 8. And then I have to actually multiply that out because it said evaluate. Okay, so I know to the 5th, that's 32, to the 6th, that's going to be 64, 128, and then 256. Of course. And then -5 to the power of 0, anything to the power of 0 is always equal to 1. And then number 11, we have -4 to the power of 0, but the negative is not included. So it's like the negative is separate and only the 4 is the base. So that makes it -1. And then, so -6 plus 1 would be -5. So it's 2 to the power of -5. So that's 1 over 2 to the 5th. So that's 1 over 32. Okay, so then we'll talk about scientific notation. Yep, 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 yep. Definitely used a lot in chemistry and other sciences. And sometimes your calculator, if you're using a calculator, it accidentally gets put in scientific notation mode. So it's helpful to understand what it's saying. All right. Okay, so basically, like on number 13, it's expressed in scientific notation. It says 8.4 times 10 to the 6th power. And you want to express that in decimal notation. So like basically normal notation. So what you're going to do is you're going to move that decimal point 6 times to the right. So you have 8.4 and you're going to go 6 times to the right. So 1, 2, 3, 4, 5, 6. And so you fill in all of those blanks with zeros. So that's 8,400,000. So yeah, so scientific notation is going to be something times 10 to an exponent. So the exponent's always going to be an integer, and the a part is going to be a number between 1 and 10. So it's always going to have basically just one digit in the ones place. and it doesn't have anything like in the tens place or beyond that. It only has like a digit has to have a digit in the ones place because it's between 1 and 10. So. All right. So when the exponent is negative, that means you're going to move the decimal to the left. So we have 3.93. We're going to move the decimal point 2 times to the left and fill that in with 0. So it's going to be 0.0393. Yeah, so when the exponent is positive, it's a big number. When the exponent is negative, it's a small number. So 7.75, and we're going to move that decimal point 6 times to the left. 1, 2, 3, 4, 5, 6. We have to fill in all of those blanks with zeros. So 0.000000775. So that's why we use scientific notation, because it's a lot easier, I guess, to write 7.75 times 10 to the negative 6 instead of 0.0000007. Especially, and it can get even way bigger than that. You know, sometimes it might be 10 to the negative 23rd power or whatever. I think there is like one of those common constants that are used in chemistry that's like Avogadro's number or something, yes. And it's like to the 23rd power or something like that. Something like that, yeah. So 5.2 and move the decimal point 3 times to the right to make it a big number. So 5,200. All right, now if you have a normal looking number and you want to convert it into scientific notation, so then we have to, so like I always just look at it and think, okay, this is a big number, it's going to be a positive exponent. 1, 2, 3, 4, 5. Positive 5, because it's a big number, it's going to be positive exponent. So it's going to be 5.7 times 10 to the 5th. Okay, now number 18, that's a small number, so it's going to be a negative exponent. Mm-hmm. 5.8 times 10 to the negative 4. So yeah, you keep moving the decimal point until you have only one number on the left of the decimal point. So 17,000. Mm-hmm. 1.7 times 10 to the 4th. Yep. 2 times 10 to the negative 2. All right. Okay, so we can multiply 2 times 3 would be 6. And then we can just add the exponent. So 9 plus negative 4 would be 5. Negative, oh yeah, positive 5. That'd be 6 times 10 to the 5th power. Oh yeah, I did forgot that part. Convert to decimal, so 1, 2, 3, 4, 5. So 600,000. So 3 goes into 6 3 times. And then 6 minus 9 is -3, so that'd be times 10 to the -3. 1, 2, 3. So 0.003. Perform the operation and express the answer in scientific notation. Okay. So 6 goes into 18 3 times. And then 8 minus 4 is 4. So 3 times 10 to the 4th. All right. I'm thinking I would convert each of these into scientific notation first and then do it. So 1, 2, 3, 4, 5, 6, 7. So that's 9.3 times 10 to the 7. And then 1, 2, 3, 4, 5, 6, 7, 8. So that's 6 times 10 to the 8. So we have to multiply 6 times 9.3. That's 55.8. And then 7 plus 8 is 15. Okay, perform the operation and express the answer in scientific notation. So, well, I know I can cancel out some zeros right away. So it's 3,300 divided by 3. So that would be 1,100. And then for scientific notation, that would be 1.1 times 10 to the 3rd. Okay, let's see here. Number 26 says, for a certain country, the bar graph shows the population of its public school students in millions and the amount that the country's government spent on public education in billions of dollars for 5 selected years. Okay, part A, express the 1980 student population in scientific notation. Okay, so we have, that's 48.1, and that is, the student population is in millions. So 48.1 times a million, basically. All right. And to write that in scientific notation, 1, 2, 3, 4, 5, 7. So 4.81 times 10 to the 7. All right. Express the amount that the government spent on public education in 1980 in scientific notation. All right. All right, let's see. So that was 97. Is that, I guess, 97.1? Okay, yeah. And that's in billions of dollars. So I have to do 97.1 multiplied by a billion. Yeah. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 9.71 times 10 to the 10. All right. Determine the amount the government spent per pupil on public education in 1980. So you have to divide. So the amount divided by the number of students. So 9.71 times 10 to the 10 over 4.81 times 10 to the 7. So I'm gonna use the calculator for this one. 9 point. You said I was a rule breaker now, didn't you? Round to 3 decimals, so 2.019. And then 10 minus 7 is 3, so times 10 to the 3rd. That's basically $2,000 per student. So $2,019 because it just says express that same answer in decimal form. All right. Number 27. The mass of one methane molecule is 2.7 times 10 to the negative 23. Find the mass of 90,000 molecules of methane. Express the answer in scientific notation. So we just have to multiply 2.7 times 10 to the negative 23rd multiplied by 90,000. So I'm going to convert 90,000 into scientific notation. So 1, 2, 3, 4. So 9 times 10 to the 4th. So 2.7 times 9 would be 24.3. And then negative 23 plus 4 would be negative 19. But I can't leave it like that because I have to, 24 is not appropriate. It has to be, I have to move the decimal point. So I have to move the decimal point to the left. So that means I would be making that a negative 20, right? Yeah, so 2.43 times 10 to the negative 20. So hang on a second. Don't run away just yet. Let me tell you something. Okay, so we basically have one more lesson, and then we're going to have a test 3, and then we're going to have the final. And I have a piece of paper that I am supposed to get y'all to like fill out. Just basically saying whether you're going to go ahead and go to 1332 or not. And let's see. I know I still haven't graded y'all's other test yet. I was trying to wait for everybody to take it first. So yeah. So if you want, I can go ahead and give it to you now, or I can wait until after I grade the second test. Then you might have like a better idea. But well, so this is the co-rec class, which means for the first 8 weeks we're doing this developmental class, and then for the second 8 weeks we're doing 1332, which is a credit level class, which is it's yeah, so it's a credit, it's contemporary math, it's a credit level math. So and it's a lot easier than most of the other it's like a lot easier than college algebra or anything like that. So